Continuing with our talk about specific types of electrophilic aromatic substitution reactions, we'll now take a look at Friedel Crafts acylation and alkylation. Friedel Crafts alkylation, we have an alkyl chloride, so this could be chloroethane or isopropyl chloride, and we're attaching the alkyl part to the ring. And we have our Lewis acid catalyst that we saw with halogenation. The same thing for acylation. We have our acyl chloride. So there's a carbonyl with an alkyl group. That's an acyl group. And then we have a chlorine attached to the carbonyl carbon. And the attachment to the ring is between the carbonyl carbon and the carbon of the ring. So for example, we could take isopropyl chloride and attach it to the aromatic ring, and the attachment should be made where the chlorine is originally on the alkyl chloride. And so we end up with isopropyl benzene. Here we're using acetyl chloride as an example of Friedel Crafts acylation. And where this chlorine is bonded to the carbonyl is we're going to replace that chlorine with the aromatic ring. So now we have a new carbon-carbon bond. So you can look at a product and come up with a plan for how to make it by breaking the product apart. We could say, well, we want to make cyclopropyl benzene. How would we go about doing that? Well, you look at the aromatic ring and where the attachment is made. So here is our attachment to the ring. This is the carbon atom on our attached alkyl group that we want to focus on. So what reagents would we need for this? We'd of course need the aromatic ring, which is just benzene. We need our Lewis acid catalyst, of course. And what's the other reagent going to be? Well, it's this 5-carbon ring. But what should we have attached here? Well, we need the chlorine. The chlorine will be bonded to the carbon that becomes bonded to the aromatic. So the net reaction is our benzene and our alkyl halide and our Lewis acid catalyst. So the mechanism, of course, is an electrophilic aromatic substitution mechanism like we've seen before, but we need to look at how the electrophiles are generated. And if you go back and look at the halogenation reactions, the method is very similar. The chlorine of the alkyl halide or the acyl chloride reacts with the Lewis acid catalyst and forms this complex. Then this falls apart and we get our carbocation, or a similar idea, carbocation, but because it's got this carbonyl, it's called an acylium ion. These are the intermediates that are electrophiles in this reaction. Once you form the carbocation or the acylium ion, that is then the electrophile that reacts in step one. Step one, the aromatic ring reacts with the carbocation electrophile or acylium ion if it's an acylation. We form our intermediate, and then we remove the hydrogen to reestablish the aromatic ring. That's in step two. Just a couple of limitations to consider. We can do alkylation or acylation. We can attach those to a ring using this method, but you cannot use vinyl chloride. Vinyl means pi bond, so the chlorine is on the alkene directly, or an aryl chloride. You cannot try to attach another aromatic ring to one aromatic ring to another using this method. So for example, if we tried to take either of these, here we have vinyl chloride, and try to add that to the ring, we'll get no reaction. Another limitation is that you cannot use, looking at the aromatic ring now, not what you're adding to it, but the aromatic ring itself, you cannot use an amino group on the ring, like aniline. If this was an NH2, or it could be alkyl groups on a nitrogen, but you cannot use an amino group or a strongly electron withdrawing group called a deactivator, which we're going to talk about in the next slides. Those make the ring less reactive. So for deactivators, it's the fact that these make the ring less reactive that this will not work. For amino groups, the reason is that the nitrogen with its lone pair reacts with the Lewis acid catalyst and ties it up, and then we can't generate the electrophile. Alkylation has a few unique problems, not that are unique to the alkylation, they don't occur for acylation. So one problem is multiple alkylations. So we could try to put an isopropyl group onto an aromatic ring, and this will work, but the product is more reactive than the original aromatic because we're going to see that an alkyl group is an activator that makes the ring more reactive. So you can put a second or more alkyl groups on the ring, so we could get double alkylation. Maybe that's desirable, maybe not. So if you try to do this, how long you let it react, so concentrations of reactants are important. You can try to limit it to one addition or multiple additions experimentally, but you're probably going to get a mixture, and you're going to have to separate them in your product mixture. Another problem that's unique to alkylation that doesn't occur with acylation is carbocation rearrangement. So in this reaction, we have propane with a chlorine on carbon 1, and so you would expect a 3-carbon chain on the ring, but we actually get the attachment at carbon 2, not carbon 1. We see there's an isopropyl group on the ring rather than a propyl group. And that's because when we form our carbocation, it's primary, and that can rearrange to a secondary.